So what we're going to be doing today are two things. We're going to be going through a quick review here of how to add and subtract fractions without using a calculator. This is very important. And you may have been taught some tips and tricks on your calculator with how to do this, but it's very tricky and you need to pay careful attention. If you follow along, it should be easy for you, but you have to focus here. So we're going to practice adding and subtracting fractions, and then what we're going to do is move on and look at something which we call tolerance, which is going to be very closely connected to precision and uncertainty, but it's a little bit different, okay? So the first thing I want to talk about, everybody, is the fact that when you have a fraction like 3 over 4, I no longer want everybody or anybody to think of that as 3 over 4. I don't want you to think of it as a fraction that way. When you see this plus this, and I want you to please and thank you to rewrite this so you have some space in between the 3/4 and the plus, okay? It's interesting, I was just about to tell you how I want you to think of 3/4. This is on page 7 of your unit handout. I want you to think of that fraction, this fraction that I'm highlighting in yellow, not as 3 over 4, but as 3/4. You've all heard a fraction expressed that way before, 3/4. And I want you to think of it as 3/4. And I'm not losing my mind, I'm just repeating myself, just like you would think of this as 3 cards. Or you would think of this as 3 clips. 3 over 4 means 3/4, okay? And when I talk about this, don't think of it as 1 over 8. Think of it as 1/8. Now, let's walk away from that for a second. This is 3/4. I'm even going to write this down. It's 3/4. And we want to add 1. This has got to be one of the goofiest words in the English language to spell, 1/8. Okay? That's what we have to add. All right. So if I told you that we have 3 puppies, I'm going to change it to 8 puppies because I don't want you to get confused and think I'm dealing with these fractions in this question. If I said we have 8 puppies and I tell you that we're going to add 3, I won't use 3, 4 puppies, what do you get? Well, other than an immense sense of pleasure, you get 12 puppies, don't you? And I'm not talking down to you. I'm getting you to understand what fractions are and how fractions work. This is 12 puppies. And if I said to you, okay, what is 30 pesos plus 8 pesos? You would say, well, it's 38 pesos. Are you with me on this? Yeah? Okay. Why are we allowed to take this 30 and this 8 and add them together? Because we're adding things that are the same. I'm adding pesos and pesos, so I add them together. Similarly, if I have 8 puppies and 4 puppies, I get 12 puppies. So now imagine that I say to you, okay, let's add this. Think about that for a second. I come in the room, I put down 12 pizzas, and I open a box, and these 14 kittens come running out. And I say, add this stuff together. You can't add it together in any sensible way. Could you say that you have 26 things? Well, yeah, but that doesn't really tell you anything. And the reason why you cannot add these together are these are different things. Pizzas are different than kittens, right? So why can we not add 3/4 and 1/8? Because they're not the same thing. I can add eighths and eighths. I can add quarters and quarters. I can add kittens and kittens. But just like I can't add pizzas and kittens, was that what I said? Yeah. Just like I can't add pizzas and kittens together, I can't add quarters and eighths together. This is why you need what's called a common denominator. This is a denominator. This is a denominator. But they're different denominators. You might as well ask me to start adding cheeseburgers and calculators together. It doesn't make any sense. So this is where the concept of a common denominator comes in. We want to arrange it so these fractions have the same denominator because then we'll be adding the same things. And in this case, eighths will be the common denominator. I can multiply, and this is why I asked you to leave some space here. I can multiply the number 4 by something to make it an 8. What would I multiply 4 by to get 8? 2. So, but I can't just multiply that by 2. I can, however, multiply it by 2 over 2, which is just 1. So I multiply the top of this by 2, I multiply the bottom by 2. How many of you remember doing this with fractions? I hope everybody, but now you have a reason why. You want to make these bottom numbers the same. So when you multiply a fraction by a fraction, that's what I have here. I'm multiplying this by this. You multiply across the top and you write the number down. You multiply across the bottom and you write the number down. So on the top, we're going to get 2 times 3, which is 6. On the bottom, I have 8. By the way, I don't, you know in junior high you did all that algebra tile stuff. Do you remember that vaguely? How many of you found it useful? Very few students do. Some do. But the idea behind fractions is that if I had the following, I'm going to come back to that in a second. So I have a pizza, and I cut it into 4 pieces. And let's just imagine it was perfect in division. Does everybody agree that that's 3/4? Okay, well, most pizzas aren't cut into 4, they're cut into 8s, aren't they? So if I cut this into 8s, are there 8 pieces now? How many of them are shaded in? 6, right? 3/4, 6/8, same thing. But the important point now is that, the important point now is that we now have a common denominator. So now what you're adding is 6/8. Don't think of it as 6 over 8. Just think of it as 6/8 plus 1/8. Well, you know, $6 plus $1 is $7. 6 goldfish plus 1 goldfish is 7 goldfish. 6/8 plus 1/8 will be 7/8. If you need to use your calculator, everybody, to figure out what number you have to multiply by to make this happen, that's fine. If you need to use your calculator to figure out that 3 times 2 is 6, that's fine. But I do not want you using your calculator with any fraction buttons. I don't want you using that method. Let's try one more. 3/8 plus 15/16. Listen to how I just said that. 3/8 plus 15/16. That's like adding 3 iguanas and 15 sand dunes. You can't do it. You can add iguanas and iguanas, or sand dunes and sand dunes. So the question becomes, can we take one of these fractions and multiply the top and the bottom by a number so that the bottom becomes what's in the other fraction in the bottom. Shanna, what would we do here?
Times it by 2.
Which fraction, the first or the second? The first one, good. So we're going to multiply this by 2 on the top and the bottom. What do we get? 6 across the top. 2 times 8 is 16. Well, now that makes sense. We're adding 16ths and 16ths. So I have 6 16ths and 15 16ths. We don't have to do this, but it might help for some of you. This is why your math teachers in earlier grades might have written something like this. Does that ring a bell? The bottom stays the same and you add the numerators? Well, that's because you're adding 16ths, so you have to get 16ths. Just like when you add kittens, you get kittens. And this works out to 21 16ths. Good? However, we don't like improper fractions when you talk about industry or manufacturing. So is this more than 1? Yeah. 1 is 16 16ths. So we have 21 16ths. What we have to do is figure out what 21 minus 16 is, because 16 of those 16ths is going to be a single one. It's going to be a whole number. And 21 minus 16 is 5. So there's a 5 16ths in here, and there's also that 16 16ths, which is 1. So when you're working in industry or manufacture and you are adding 3/8 and 15 16ths, what we want to do is say you get 1 and 5 16ths. Don't let that little thing bring you down. If that's really the bothersome part for you right now, but you understand how to bring them together with a common denominator, that makes me happy. Okay? Okay, so how are we going to do this? 2 1/4 plus 3 16ths. What we're going to do is say that this is 2 plus 1/4 plus 3 16ths. We're not going to worry about the 2. We know what 2 is. 2 is 2. At the end, whatever we get, we're going to say 2 and that amount. What we want to focus our attention on is this. And I don't know if you've noticed, but you notice all our fractions are quarters, 8ths, 16ths. That's because that's what you use on a tape measure in imperial. Dylan, is there one of these fractions at the bottom we can multiply by a number to get the number that's in the other bottom? And which fraction would we multiply? The first or the second? And what would we multiply it by? 4, good. I need to multiply this 4 on the bottom and this 1 on the top by 4, because on the bottom 4 times 4 is 16. So what are we at then? We have the 2 plus 4 over 16 plus 3 over 16. And I don't know if you realize that I just broke my rule. I just called it 4 over 16 and 3 over 16. It's 4 16ths and 3 16ths, which tells us it's 7 16ths. So this is 7 16ths, and it's 2 and 7 16ths. How many of you take any kind of vocational courses where you have to measure using a tape measure and measure things like that, right? You go to the 2-inch mark and then you look at the 7 16ths mark. And by the way, there's a reason why fractions are used in industry. If I told you that you need to plane the shelf down in your planer so that it's 2.4375 inches thick, how do you even measure that? Well, it turns out that's 2 and 7 16ths. Bless you. That's the first thing I want to go over today. Now let's talk about the second thing. So you're going to turn the page, or is there one more example? There is. Okay. Ooh, a subtraction. 4 and 9/16 minus 3/8. So what we're going to do is just park that 4 over here. We'll worry about that in a bit. I cannot take 16ths and subtract 8ths. That's like me giving you a basket of kittens and saying, we're going to remove 3 puppies. It makes no sense. Keldon, what would our common denominator be here? Do you know? What would we multiply one of these fractions by to get this by 2? And it's going to be which fraction? Good. So we're going to multiply this by 2 over 2. And we get 4 plus 9/16 minus 6/16. We're on page 7 right now, Ryan. And just like if you had, and I know this might get repetitive for some of you, but be patient because I want it to be so that everybody gets it, not just you. Just like if you had $9 and subtracted $6, you'd have $3. When you have 9/16 minus 6/16, you get 3/16. So our answer is 4 and 3/16. Are we okay with that last example? Okay, I want you to turn the page now. And this is the thing that, you know, as much as, this is on page 8 now, as much as I taught you about precision and uncertainty again and again and again, until it finally sunk in, we may have to do that even more with what we're going to be talking about for the rest of the unit. And for the rest of the unit, we're talking about tolerance and what's called a nominal value. And I might as well start off the lesson by telling you that the word nominal means ideal. Okay? The word nominal means ideal. It's what you're aiming for. And this is all about industry and manufacturing. So a nominal value is the ideal value. When you're making something, when I'm manufacturing something, let's say, I'm just trying to think of something I'm working on at home right now. I'm building some shelves at home for my basement to put some tools on. And I have a certain amount of distance along one wall, and I've put up the rails, and I've put little shelf brackets in there. So now I have to cut the shelves to a certain width so they fit in there. Now, is there an ideal value for the shelf? Sure, there's a value that I'm going to measure. I'm going to say, well, I want the shelf to be 32 inches deep. But does that mean I have to cut it exactly 32 inches? No. But the 32 inches is the nominal value. If in a perfect world I could measure it exactly, that would be the ideal value. So this is what you're always aiming for. We'll get to tolerance in a bit. So when products are manufactured, a range of measurements is acceptable. Not a big range. If I want those shelves to be, I've forgotten already, 32 inches deep, does that mean there's a range of values that are acceptable? Sure. Can I cut them 8 feet deep? No. Can I cut them 2 inches deep? No. It has to be within a certain range. That range is called the tolerance. Now, some of you are going to start seeing a connection between what we're doing today and precision and uncertainty. Let's say, just as an off-the-cuff example, not an official example in your notes, that the smallest length that would still work, I don't care what we're talking about, the length of a little dowel, the length of a screw, whatever. The smallest length that will still work is 11 millimeters, and the largest length that would still work is, I don't know, 14 millimeters. Let's say that what I've done is I'm building a cabinet and I've drilled holes in there to a certain depth, and I'm going to use little wooden dowels and glue those parts to another part with the dowels. You with me? You realize the dowels can't be this long. But the dowels also can't be this long, because if they're this long, if they're little tiny dowels, there's no support. So I'm telling you that the smallest length that is acceptable is 11 and the largest is 14. The tolerance, who can tell me what the tolerance is? Take a chance. I don't know if anybody can, but if you can, that'd be great. It's 3 millimeters. It doesn't tell you anything at all about the length that you want, but what it's telling you is the difference between the maximum and the minimum. In the previous section, we would have said something like the range of values is this number to that number. Here, when we talk about tolerance, you actually subtract those numbers. So there's a tolerance of 3 millimeters. You can be 3 millimeters in either direction. Thank you, Ryan. So the concept of tolerance is important because when you install and put parts together, they have to fit together right, they have to work properly, and maybe they want to look right. I mean, the first cabinet I ever made, it fit together right, but it looked like garbage. Everything was all crooked. The nominal value is the target value. So I don't know, but I'm going to ask, if this is the largest length and this is the smallest length, what do you believe the nominal value is? The ideal value. This is acceptable, 14. This is acceptable, 11. Addison? Excellent, it is 12.5. And I'm going to write that down. And I'm going to ask how you got that, because there's two ways, at least two ways you might have thought of this. So how did you come about at the number 12.5?
I divided the tolerance by 2, but also I double-checked that it was like the middle number of the largest and smallest.
Perfect. So what you're recognizing, and again, I'm just kind of, as I say, off the cuff explaining this, is that there's a minimum value, there's a maximum value, and if I'm saying the nominal value is the ideal value, then it's halfway in between. Number one, the size of a dowel that's used in a cabinet can be as small as 11.5 and as large as 12.5. What is the tolerance? So you need your calculator for this. What are we going to do to find the tolerance here? Jamie? Can you sit up, please, and pay attention? Thank you. What are we going to do to find the tolerance? Alex, do you know? What did we do to find the tolerance when I gave you this example? The smallest length was 11, the largest was 14. How did we get the tolerance of 3? Exactly, we minused. So you're going to take the maximum, which is 12.9, and subtract the minimum, which is 11.5. Okay? So that's how we find the tolerance. Let's write that down. I think we can leave out the units until we get to the end. What does that give us, Kelvin? 1.4. So the tolerance is 1.4 millimeters. How do we find the nominal value? This is not simple. It's not simple. What you need to do is recognize that that tolerance is the distance between the minimum and the maximum. So there's a lot of ways to do this, and I didn't explain the second way to do it, but there is another way. This is 11.5, and this is 12.9. This distance between them, everybody, is the tolerance, and it's 1.4 millimeters. I keep writing meters here. I meant to write millimeters. So if you follow Addison's method, she would divide the 1.4 by 2, correct? And get 0.7. Let's do that. Let's make sure we know how to get 0.7. What we're going to do is find out where the middle of this line is. So 1.4 divided by 2 . So Meadow, can you calculate that for us? 1.4 divided by 2. Good. 0.7. What that means is that from the middle, which is the nominal value, to here is 0.7. And from the middle to the maximum, which is here, is 0.7. So you have two options here. We can take 11.5 and add 0.7 to take us to the middle. Do that for me, please. Zedric, what do we get when we add 0.7 to 11.5? 12.2. 12.2. So if we've done things right, this is 12.2 millimeters. But we can do the check that Addison was talking about, which is, well, take that 12.2 and add 0.7. And if it's right, then we should get 12.9. Do you get 12.9 when you do that? Try it. What do you get when you take 12.2 and add the 0.7? Does it take us to here? Because if it does, then we've found the middle ground. Okay? Or you could take 12.9 and subtract the 0.7 to see if you get this nominal value. I'm going to show you a different way you could do it. Okay? Average these two numbers. Add them together, hit equals, and then divide by 2. So on your calculator, we're taking, Alex, do you have a calculator? On your calculator, you're taking, I'm asking you to take 11.5 and add 12.9 and then divide by 2. Does it give you 12.2? It does. The problem is this. I think if you use Addison's approach, it makes sense. She understands why what she's doing works. You might not understand why averaging the two numbers works, but it works basically because you're looking at the middle, and when you average two numbers, that's what always happens. You find the middle number. Just like if you had 68% and 72% on two exams and I wanted your average, I would add them and divide by 2. That would be the middle. I'm going to end it there today. And I want you now to turn to page 16 of your unit handout. And a couple of you have some other things to catch up on here. Well, if you get done early, you get done early. That's fine. I'm worried that if I go on so that you have more work to do because I need to teach you something else, I'm worried that I'll just fill your heads. So all we're going to do is the fractions question number 1 on page 16.